All right, students, good morning. This is a lesson on analyzing the five properties of minerals. Let's just jump right in. So, first off, all rocks are made of minerals. There actually are a couple rocks that aren't, but for the most part, almost all rocks are made of minerals. So, minerals are not rocks, but rocks are minerals. Here's a picture showing exactly that. We have some metamorphic rocks, igneous rocks, sedimentary rocks, and these are the minerals, some examples of minerals that you might find in those rocks. So the minerals make up the rocks. There are five properties that all minerals have. In order for something to be classified as a mineral, it has to basically have these five properties. So the first one is it has to be naturally occurring. That doesn't mean that humans can't manipulate a natural process to grow a mineral. For instance, if you have some salty water and you evaporate the water, you'll have some salt crystals left behind. Well, that's still a natural process, but you kind of manipulated nature in order to make those crystals. Here we have a cave with just absolutely monstrous, looks like gypsum, maybe or calcite crystals. And this is a limestone cave. Most caves are made up of limestone. So lots of calcite everywhere. Here's what I was talking about. You get some salty water. You just load it up with lots of salt. Let it, let all the salt evaporate. Let all the water evaporate, and what's left behind are these little cubes of salt. Here's a really cool video showing sodium acetate growing. You can see how once a seed is added, it's called a seed, the mineral will grow, spontaneously. And you can see how it's growing. It's growing in in this spiky kind of way. Okay. Two other properties: it has to be inorganic, meaning it can't be alive. That doesn't mean that living things can't make minerals, because they definitely can, like bones, teeth, or shells of organisms. Those are all minerals, but the mineral itself cannot be alive. It's got to be solid. It can't be a liquid or a gas. And here's the really, really big ones. These two are really, really important. They have to have a crystal structure. And when we say a crystal structure, we mean that the atoms are arranged in a specific way. And there are only so many ways an atom can be arranged. Only so many ways that atoms can be arranged into a crystal. And here are the 7 crystal families. Now, you don't have to know that. This is definitely college level stuff, but you can just check it out. This is kind of higher level, higher level understanding of what minerals are at the crystallographic level. Okay. And the atom arrangement is what makes the characteristics. The arrangement of the atoms is what makes the characteristics. And here's a perfect example of that. We have diamond over here and we have graphite over here. They're both made up of carbon atoms. So they're both made up of the same composition. They're both carbon. However, diamond is in no way like graphite. In a lot of ways, they're actually the exact opposite. Right? Diamond is generally translucent. You can see right through it. Graphite is like a gray, kind of metallic. Right? Diamond is extremely hard. Graphite is incredibly soft. And diamond's super expensive. Graphite is relatively inexpensive. All right, what's the reason for that? It all has to do with the atoms and how they're arranged. So you can see here we have covalent bonds, and the atoms are arranged in kind of a network. Whereas over here, graphite is arranged in sheets. We have a sheet, sheets of graphite, and they're weakly held together by a force, Van der Waals forces. So they're very, very weak, which is why you can take your pencil and rub it across a piece of paper and get a mark. You're actually rubbing off those sheets of carbon atoms every time you use your pencil. Diamond, you can rub it and it just will not do that. Again, the atoms are arranged in a unique way, and that makes the characteristics. The most common arrangement of atoms for minerals is the silica tetrahedron. It's the most common arrangement of atoms in the crust, especially. And it's the most basic compositional so composition being silicon and oxygen, and structural, meaning that pyramid of all silicate minerals. And silicate minerals are the family of minerals that make up most rocks in the earth, especially in the crust. And you can see how it's like a pyramid shape. So it's in a tetrahedron shape. It's 4 oxygen atoms with a silicon atom in the center. Okay. If we go back to the first page of the reference table, you can see how the 2 most common elements in the Earth's crust are silicon and oxygen. So it makes sense that that would be also the most common arrangement, or most common composition in the Earth as well. Just to kind of make a connection between the silica tetrahedron is SiO4, and look right here, that's the most common elements, 2 most common elements in the crust. There's a connection there. So if you bond these individual tetrahedron together, you can get lots of different arrangements. You can get minerals that have isolated tetrahedra. You can have sheets of tetrahedra. You can have a single chain of tetrahedra, framework, double chain. These are all, again, the arrangement of the atoms, the arrangement of the tetrahedra will determine the mineral's characteristics. The last thing a mineral has is a uniform chemical composition, meaning that the elements that make up that mineral are the same throughout, for the most part. So quartz, for instance, this quartz crystal, it's primarily made up of silicon and oxygen. That's what makes it quartz. If we were to change its composition, somehow it would no longer be quartz, it'd be something else. So again, the chemical composition is also, that uniform chemical composition is what's also defining it as a mineral. All right, that's it for the lesson, and I will see you all tomorrow.